Okay, good morning, all of you. It's a pleasure to welcome you all today, this morning. And it's a pleasure to welcome Professor Gulab Dewangan from Ayuka, our friend and colleague from Ayuka. He works largely in the high energy part of the electromagnetic spectrum, X-rays, where he works on a variety of compact objects, but especially on active galactic nuclei. And he's been closely involved with a very large number of astrosat projects, which has yielded a number of very interesting results on active galactic nuclei, often referred to as AGN in short. So it's a pleasure to welcome Mr. Dewangan. So Gulab.
Thank you very much, Professor Sakya, and good morning to all. So today I'll be talking on active galactic nuclei. So the first question is usually, what are these active galactic nuclei? And in order to understand that, we also need to think of normal galaxies, because there are different types of galaxies. Some of them are active, some of them are normal galaxies, and there are also different types of normal galaxies. But for our purpose, if you let's say if you take an image using a telescope, and let's say you use a very short exposure, let's say, and you're observing a normal galaxy, what you will see, initially you may not see anything because the exposure may be very short, but if you keep on increasing the exposure, then you will start seeing a diffuse emission. Okay, of course the central region will be brighter, but overall you will start seeing diffuse emission. But if the galaxy contains an active nucleus, or if the galaxy is an AGN, so in the short exposure, what you see is a point-like or a star-like object. Okay, and when you start increasing the exposure time, this point-like object will become brighter and brighter, and you will start seeing the host galaxy also. For example, in the left-hand side, I have put a picture of an active galaxy NGC 4593. Here, you see a very bright nucleus, and of course, the spiral arms. In the right side, there's a picture of a normal galaxy NGC 3277, and here you see a lot of diffuse emission. The central region is brighter, but this is not an active nucleus, only because the central region is more bright. That's why you see this somewhat higher luminosity, but this is not really an unresolved point source, unlike in the case of AGN. So by the way, the left hand side picture of NGC 4593 was taken with the AstroSat near ultraviolet, the AstroSat ultraviolet imaging telescope in the near ultraviolet band. So AGNs have a very bright nucleus, and that is some kind of an energy source other than the stars, and this sometimes dominates the nuclear emission. Sometimes dominates the light from the host galaxy, sometimes, but not always. So this is one sign of an AGN, but there are other signatures of active galactic nuclei. So essentially they are nuclei of galaxies that are active, and that host an energy source other than the stars. Okay, and this activity is revealed in observations in a variety of ways. For example, we have, of course, a high luminosity from a point-like source, but in addition, one can have jets, relativistic jets emanating from the central nucleus, and seen something like this. So they are, of course, they cannot be attributed to stars, and this origin of the jets are non-stellar in nature, and this is again a signature of an active galactic nucleus. In addition, there are other observations. For example, if you take the spectrum of the nucleus, then you will see emission lines in the ultraviolet bands, and sometimes you see very broad emission lines, which is not observed from normal galaxies, and that's another signature of AGN. Sometimes some of the AGNs may be obscured. The central region of AGNs may be obscured by dust lens. For example, in this case of NGC 1365, you do not see a very bright like nucleus, but there is a central dust lens passing through the center, and it looks like a normal galaxy. But if you observe the same galaxy in X-rays, then you see a very bright nucleus here, because X-rays can penetrate the obscuring material here, particularly somewhat harder X-rays. So you see a very bright nucleus, and that's another signature of the presence of an active nucleus or active galactic nuclei. So there are a number of different types of AGNs, but we can classify them in three main types. We are not going to detail in the classification scheme because that will take a couple of lectures itself. So the main type of AGNs are the Seaford Galaxies, and they are so called because Carl Seaford discovered this type of AGN. So this type of AGN have this bright nucleus, and the luminosity of the nucleus itself, or the active galactic nucleus itself, is comparable to the luminosity of the entire galaxy. Okay, then we have radio galaxies, and they are radio loud objects. Essentially, they have much more radio luminosity compared to what we observe from normal galaxies like our own. And I think you already have lectures on radio galaxies, and I'm not going to go into detail in the radio galaxies. But just to say that they are much more powerful in the radio band, and they show jets emanating from the nucleus, and many of them have the jet and lobe structures. Okay, then the other major type of AGNs are these quasars, or QSOs. There are nowadays they are simply called as quasars. They can be radio quiet or radio loud. Okay, so but if you just look at the nuclear luminosity, the luminosity from the active nucleus itself, that is actually much more compared to what we observed from Seaford type AGN. So the luminosity of AGN in this case is about 100 times the luminosity of the entire galaxy, containing something like 10 to the power 11 stars or so. So these objects are really powerful, and that the powerful emission is just arising from the nucleus, and that is why they are called active galactic nuclei. So going into a little more detail about the Seaford galaxies. So if you look at the optical spectrum of Seaford galaxies, so here it looks like what I have shown in this slide. So first of all, if you look at the continuum emission, so this is a very strong continuum. Continuum emission is not zero, it's a strong continuum. Then you would immediately notice that there are very broad emission lines like this. This is due to the H alpha emission at 6563 angstrom. Similar lines are there again due to hydrogen. This is H beta lines. So the H alpha, H beta, S gamma, H delta, all of them are actually broad lines, and they are the Balmer lines. Okay, and there are other kinds of broad emission lines, particularly in the ultraviolet, for example, carbon 4, magnesium 2, which are not shown here. But apart from the broad emission lines, you also see very narrow emission lines. For example, here you see this oxygen, the emission lines, the narrow emission lines from oxygen 3 at a wavelength of 5007 angstrom. Similarly, there are other narrow emission line due to oxygen 2, 3727 in the H alpha band, almost blending with the H alpha broad emission line. There are this nitrogen 2, 6583 emission. There is also this oxygen 1 line at 6300. So the characteristic of these AGNs is what is observed in the optical spectra is they have very strong continuum. They have broad emission lines, and they also have narrow emission lines. Now, one can convert the width of these emission lines using Doppler shifts, because the wavelength is shifting compared to the central wavelength. And it turns out that the width of these broad emission lines can range from, let's say, a few thousand kilometers per second to tens of thousands kilometers per second. So the material which is emitting these broad emission lines must be moving with several thousand kilometers per second. Then only we can observe this kind of broad emission lines. But on the other hand, the narrow emission lines, if you convert the width of these narrow emission lines, they are only about 500 kilometers per second. So there are at least two kinds of line emitting material in these objects. One is moving very fast, of the order of, let's say, 5 to 10,000 kilometers per second. The other kind of clouds which are emitting, they have roughly about 400, 500 kilometer per second speeds. Okay, this is the lower panel, is essentially the expanded view of the spectrum here. Here you will see all these lines, etc. But there is a sharp rise below 4,000 angstrom. This is called smaller blue bump, small blue bump, and that means there is also big blue bump, which we will discuss later. But this is a small blue bump, or this sharp rise, southward of this 4,000 angstrom, is due to these two things. This is Balmer continuum and the iron-2 emission. So Balmer continuum, whenever the electrons join from the continuum of the hydrogen atom to n equal to 2 level, then that gives rise to some kind of continuum emission. And that plus this iron-2 emission, iron-2 again has a very large number of transitions. The combination of these two things actually creates this kind of rise, southward rise below 4,000 angstrom. So let's look at the typical other signatures what we observed, and that helps us in classifying these objects as active galactic nuclei or active galaxies. I had mentioned they have active galactic nuclei are essentially point-like. They are unresolved with these telescopes what we use. This means that their size is actually much smaller than about one parsec or even one light curve. So the huge amount of luminosity is just arising from a very compact region. Here are the images of the central regions of some of these active galaxies taken with the Hubble Space Telescope. You see very bright nucleus in everywhere. But in addition, there are some structures. So these nuclei are surrounded by a variety of forms. For example, sometimes you see the dust lanes. Sometimes you see some kind of a ring here. There are a variety of some of the structures. So we do not clearly understand the origins of these structures surrounding this brilliant nuclei, but probably they may be carrying some clues how the central engine is actually powered or fed. Yes.
So, which frequency range is these images taken in?
These are optical images.
Oh, these are optical.
Yes. The nucleus, the unresolved nucleus, has very large luminosity that can range from 10 to the power 42 to 10 to the power 48 ergs per second. And if you compare this luminosity with the luminosity of our sun, then these nuclei have a luminosity of 10 to the power 9 to 10 to the power 15 times the luminosity of the sun. To make sense of these numbers, let's compare with the luminosity of a normal galaxy or a filled galaxy. Like let's say Milky Way. If you look at the Milky Way, has of course something like 10 to the power 11 stars, and let's roughly assume that all stars are emitting like our sun. Then Milky Way has a luminosity of something like 10 to the power 44 ergs per second. So the AGN luminosities range from, let's say, 1/100th of the luminosity of an entire galaxy to about 10,000 times the luminosity of a typical galaxy. That's the range of the luminosity from the active galactic nucleus itself. Of course, so when we measure this luminosity, there are certain complicating factors. For example, there can be large extinction, so we may not be measuring the real luminosity, but lower than actual luminosity. Then the relativistic beaming, if there is a relativistic beaming, that can also affect the measurement of luminosity. In that case, we will measure more than actual luminosity because the radiation is beamed towards us. Another very important...
this luminosity is integrated over the visible spectrum, is it?
Yes, this is mainly measured in the visible band. Okay, but if you integrate over that, because I will discuss it later, the the luminosity from AGN is dominated due to one particular component, which we call the big blue bump, and that emits in the optical ultraviolet. Okay, so particularly in AGNs which are unobscured. So mostly, I mean, if you integrate, it will be somewhat larger, maybe by factor of 5 or 10. But usually, this will be the order in the optical band. Another very important characteristic of the AGN is this broadband continuum emission. Again, to make sense, we will need to compare with the broadband continuum emission from a normal galaxy. Let's look at the normal galaxies. The solid line showed here is essentially the spectral energy distribution of a normal galaxy like our own. And here in this plot, the x-axis is the frequency, log of frequency, and y-axis is log of the flux, f nu here. So the luminosity or the emission from a normal galaxy is confined roughly in a frequency range, which varies by a factor of 10 or so. What is the reason? Because normal galaxies have essentially the emission from normal galaxies is from stars. And stars, of course, there will be low mass stars and high mass stars. And roughly the temperature of the lowest mass stars will be 2000, maybe 3000 Kelvin or something like that. While the hottest stars will have something like 30,000 or 40,000 Kelvin. So the temperature of these stars is varying by a factor of 10 or so. Okay, so what this means is that these stars are emitting like black bodies. So if you sum the black body emission from the low mass stars and the high mass stars, or the cool stars to the hot stars, there the emission ranges from let's say from near infrared to ultraviolet. Okay, that's where the emission will usually ranges. On the other hand, if you look at the spectral energy distribution of an AGN at a nearby AGN, for example, this NGC 3783. So first of all, the emission is not confined to a narrow range in the frequencies. You will see, in fact, in the ultraviolet, the emission from the normal galaxy is going down, but in the ultraviolet, actually, the emission from AGN is going actually increasing, and it does not diminish, it does not decrease at high frequencies in the soft and hard X-rays. It continues. There is a strong emission in the ultraviolet, in the soft and hard X-rays, at least down to even to gamma ray energies. Okay, if you come to the infrared and radio side, again in the infrared, again the luminosity of this AGNs is increasing compared to normal galaxies. So there is something called the IR bump or the infrared bump. And when you go to the radio part, and there are radio quiet AGNs and radio loud AGNs. This particular one is radio quiet. The radio luminosity is actually low, but in radio loud AGNs, the radio emission is also high. So if you look at it, this is somewhat more detailed spectral energy distribution from AGNs. So in the radio part, the radio luminosity is also high from radio loud AGNs, while from radio quiet AGNs, it is much smaller. So if you look at the spectral energy distribution of AGNs, there are three main components. One of them in the optical ultraviolet band is called the big blue bump, and we will discuss the origin of this big blue bump. And in the longer wavelength side, there is another bump which is called infrared bump. And of course, there is a radio emission. At high frequency side, in the soft and hard X-rays, there is another component which is strong, and which looks like more like a power law component, and which cuts off at a high energy about 100 keV or so. So these are the main components. And when we are talking about, let's say, radio quiet AGNs, then these are the three main components. And we will discuss the origin of this, at least the primary continuum here. Okay, the primary emission from AGN is considered to be this big blue bump emission, then the emission components in the X-ray band. The infrared bump is essentially thought to be the reprocessed emission of this ultraviolet as well as X-ray emission by something called torus, which we will see later. Okay. So let's look at okay, the other characteristics of AGN. So I mentioned that this AGN show very strong emission lines, and if you compare the optical spectrum of let's say a normal galaxy and AGN, for example, NGC 4151, 4953, in normal galaxies, first of all, the continuum is extremely weak, very weak. You see this noisy like thing. That's because the continuum itself is weak. And then there are some absorption features. Of course, they arise from the stars. On the other hand, the AGNs have very strong continuum and broad as well as narrow emission lines. So based on their appearance of this, whether there are broad emission lines or narrow emission lines only, the AGNs have been classified in different types. For example, type 1 AGN or the Seaford 1 AGNs have both broad and narrow emission lines, while the type 2 AGNs only have narrow emission lines. The type 2 AGNs do not have the broad emission lines, which we see in type 1 AGNs. And some of the the radio loud AGNs, some of them also show this broad emission lines. So in that case, we call broadline radio galaxies, and a number of them do not show this broad emission lines. In that case, we call them as narrow line radio galaxies. In addition, there are other types of AGNs. For example, there is a class of AGN called blazars, and one type of blazar is this object called BL-LEC object. Here, you see extremely strong continuum emission, and you almost do not see any kind of emission absorption lines. There are some there may be some weak emission features, absorption features, but these spectra are almost featureless. So the featureless spectrum is thought to be dominated due to the jet emission from the jet, and where the jet is pointing towards us. In such a situation, relativistic beaming dominates, and even though there may be the emission lines, whether it sometimes maybe broad or narrow emission lines, but the continuum or the jet emission in this particular case is so strong that it dominates everything, and the observed spectrum becomes featureless. Okay, so this is here I show the mean quasar spectrum. This is essentially the spectrum formed by taking a mean of spectra from large number of quasars. And again, the quasars also show broad emission lines, something similar to what we see in Seaford 1 type AGN. Okay, so these are the basic differences, are the different types of AGN classified based on their optical emission line properties.
Can you please again explain like how to identify the blazar?
Blazar, so if you take an optical spectrum, the blazar spectra, particularly blazars have two types. One is BL-LEC type. So BL-LEC type AGN, the blazars do not show strong emission lines. The continuum is extremely strong, but the emission lines are not present, or even if they are present, they will be extremely weak. Okay, that's how we identify
there is no emission lines.
Sorry?
There is no emission line.
There are no strong emission lines. There may be extremely weak features, but you can say that the emission lines emission or absorption features are absent in the optical spectra of BL-LEC types. The blazars also have a different type called FSRQs, flat spectrum radio quasars. In that case also, the continuum is extremely strong, but those objects do have broad emission lines. So again, in these two types of AGNs, people think that the emission is dominated by the emission from the jet, which is essentially continuum emission.
So, but you said that one of the important ways to recognize is through their emission line. So, how do we know it's an active galactic nuclei type if there are no strong emission lines?
continuum. So in that case, you look at the continuum emission and compare with the spectrum of a normal galaxy. Normal galaxies will have very weak continuum and the absorption lines, but BL lake type agents will have very strong continuum. And the BL lake type objects are actually identified from their radio emission, from their emission from the jet, which is dominated in the radio band, and even in gamma ray band, for example. So one uses different information. How does the optical spectrum looks like? Whether it is a purely kind of a more like a continuum, then of course you say, okay, this is likely to be blazar. Then you look at the emission in other X-ray, gamma ray band, and then you obviously confirm, okay, what could be the nature of this objects. Okay, so again, also you have to, yeah.
What is the source of the continuum emission? Just to be clear.
Yeah, so you see, the blazars have relativistic jets, and in fact, most radio loud agents, almost all radio loud agents, have a very strong jet emission, and the jets are thought to be relativistic. That means the particles in the jet are actually moving with relativistic speeds. And if the jet is pointing, let's say, away from us, then because the jet is moving with relativistic speed, the emission from the jet is actually beamed along the direction of the motion. So if the jet is pointing away from us, in that case, most of the emission is directed away from us. So then we are not looking the very strong jet emission, but we are looking the central engine, and that's why we have the emission lines, narrow emission lines, broad emission lines. But now imagine if the jet is pointing towards us. That means the emission from the jet is beamed towards us. And that emission we are observing is the featureless continuum. And the source of this emission, or the origin of this featureless spectrum, is due to the jet emission.
Okay, so it's the synchrotron radiation.
In the optical band, it will be synchrotron, radio, infrared, optical, ultraviolet. This will be synchrotron emission, even in the soft X-rays. But when you go to hard X-rays or gamma rays, the emission can be synchrotron, self-Compton, or external Compton, etc. Yeah, but in optical, you can assume this is a synchrotron emission.
Okay, thank you.
Yeah. Yet another very important characteristic of AGN is the variability of their light output. If you look at, let's say, the X-ray emission and observe the AGNs as a function of time, and then you measure the X-ray intensity as a function of time. So this is one example from IRAS 13225. This is a Seaford type 1 AGN. And look at how the X-ray intensity is varying. It's increasing suddenly and going down in this is in time. This time is in days, but we have seen this variability by a factor of 2, even in thousands of seconds. And here you see the variation is by more than by about more than by a factor of 100, more factor of almost 200, 300. So this is some of the agents so huge, really huge variability. If you look at the optical, the ultraviolet continuum emission, for example, this is the continuum emission measured at different wavelength: 1350 angstrom, 1840, 2670, and 70 angstrom from this Seaford galaxy called NGC 5548. Again, this continuum, this intensity in the continuum is plotted as a function of time, and you see again this strong variability of the ultraviolet continuum emission. Now, if you look at the ultraviolet line emission, and the variability from optical line emission will be similar. This is the carbon 4 intensity, Lyman alpha line intensity, magnesium 2 line intensity. Again, you see this strong variability of the line emission as well. And now if you look at the radio emission as a function of time, this is again from the BLEC type object, which happens to be a blazar. The emission is very strongly variable. The blazars are highly variable agents. So The agents generally vary in at almost all web bands. This is very important characteristic. Okay, just to summarize the various different types of properties of agents. Of course, whatever we discuss, not all agents will have all the properties, but some agent will have some of the properties. So first of all, the agents have a large luminosity. Luminosity can range from 10 to the power 9 to 10 to the power 14 times the luminosity of sun. The emission arises from extremely compact region. The sizes are much less than 1 parsec or so. They have a very broadband continuum from radio to gamma rays. They have very strong emission lines in the optical and ultraviolet. They emit strongly in the X-ray band, and many of the agents are also very strong at gamma ray wavelengths. They show strong variations over the almost over the entire electromagnetic band, with a range of time scales. The variability time scale can range from minutes to days and months, of course. And the radio loud agents, of course, have the jets and lobes. And I'm not going to discuss in detail because you already have a talk. And these jets and lobes can their sizes can be very large, from kiloparsec up to kiloparsec, megaparsec scales, etc. Okay, so let's now try to infer what is the origin of the power source. How does the huge power or the huge luminosity is arising from these agents? So this, of course, we have to infer from what we have in our hand in terms of from our observations. So one of the thing is that the agents are highly variable, and we can use the variability time scale to infer the size of the emission region, because we cannot resolve the nucleus with our telescope, so we cannot actually measure the size of the emitting region. But there is a handle one can use the variability time scale and put limit on the size of these sources. So first of all, assume that the state of the emission region is changed by a physical process, because if the luminosity is increasing, that means there is a change in there is a state change or the change in the physical process. So in such a case, there are two time scales which are important. One is the time scale for the radiation process, this tau process. Let's say if you're talking about synchrotron radiation, for example, when the particles are accelerated, and this radio emission is arising, or radiation in the synchron emission in the optical UV bands arising, what would be the kind of time scale? And then let's say the another time scale is the crossing time scale. Let's say we have some kind of a spherical region, just to assume, and this, let's say, imagine that something happens at the center, so that due to the change in the physical state of the object, the radiation increases due to some radiation process, and so there is a disturbance at the center, let's say. And because if a tiny region, only the center is emitting, we will not observe huge variability. So that variability has to be caused by almost the entire emitting region. So that means the disturbance which started at the center has to travel to within the spherical region up to the outer region. And that's the crossing time scale. And this crossing time is generally much longer compared to the time scale for the radiation process. And if whatever is the speed of this speed with which this disturbance travels from let's say from the center to the outer region, that of course cannot exceed the speed of light. So that state change spreads with a speed v, let's say, which is less than the speed of light. Then one can say the size of the emitting region, which let's say this is L, then that will be the v speed of the spread change, that v, and the crossing time delta t. So that this quantity v into delta t will of course be less than c into delta t. Delta t is crossing time again. Okay, but our observed time scale will be the sum of these two time scales, the tau process and delta t. And as I mentioned, the tau process is much smaller than delta t. In any case, one can say that the size of the emitting region is less or equal than the speed of light times the observed time scale. Okay, and when you use this information then we can infer the size. For example, in the optical ultraviolet, particularly radio quiet AGNs, we observe the variability time scale is typically 1 to 10 days. Okay, and that translates into a size scale of 0.001 to 0.01 parsec. You see, it is much smaller than 1 parsec or 1 light year. On the other hand, if you look at the variability time scale in the X-ray band, the X-ray emission varies on much faster time scale. The time scale is about 1 hour for many AGN, and this time scale of 1 hour translates into a size scale of very small, 10 to the power -5 parsec or so. And if you compare this kind of size scale with, let's say, with the Schwarzschild radius of a black hole, then what you see is that the size scale is comparable to the Schwarzschild radius of a supermassive black hole. Let's say about 10 to the power 8 solar mass black hole. The size scale will be like 10 to the power -5 parsec. So this may suggest that the variability, particularly in the X-ray band, is occurring in the vicinity of a supermassive black hole, and this is what now it is thought. So yeah.
So why is there such a huge difference in time scale in both X-ray and optical?
Yeah, so you can imagine that the X-rays are arising from the innermost regions where the size is smaller. Then the optical emission are arising from a larger region, maybe surrounding the X-ray region. So that is why if the size of the imaging region is larger, then the variability time scale will be large.
Inner region means that a vicinity of those black holes, right?
Vicinity of the black hole. Yeah. So we will look into some of those scales with some schematic pictures, etc. Okay. So after, of course, a lot of studies, we have some kind of a physical picture of AGN now, and very basic ideas or arguments are as follows. First of all, AGNs have high luminosity. As I mentioned, AGN's luminosity can range from 10 to the power 42 to 10 to the power 48 ergs per second. And if you think any object cannot emit arbitrarily large luminosity, so what is the reason? Because, okay, of course, the large luminosity means a huge number of photons are being emitted. These photons will interact with the surrounding material, particularly with the electrons through Thomson and Compton scattering. So this high luminosity will result in radiation pressure force on the electrons, and the electrons and protons are coupled. So this the radiation pressure force will throw out the material if the luminosity exceeds some value, which the material will also be bound due to the gravitational attractive force. But if the luminosity is high, the luminosity will exert radiation pressure force, and that will try to throw out the material. And when you equate the outward radiation pressure force and inward gravitational force, then you get a luminosity. You derive a luminosity, something called the Eddington luminosity. And this Eddington luminosity is, of course, a function of the black hole mass. So it is roughly about 1.4 times 10 to the power 38 ergs per second for one solar mass object. Okay, and now in AGNs, we are observing something like 10 to the power 44, 10 to the power 45 ergs per second. So if you substitute this, let's say 10 to the power 46 ergs per second or so then you automatically get the huge mass, 10 to the power 8 solar mass or so. If it is 10 to the power let's say 48 ergs per second, then you get 10 to the power 10 solar mass. And if you have, let's say, 10 to the power 44, so then you get a million solar mass. So just with a very simple observation and very simple physics, one can infer that the AGNs must be hosting a supermassive black hole with a range with black hole mass from 10 to the power 6 to 10 to the power 10 solar mass or so. Okay, even smaller, sometimes 10 to the power 5 or 10 to the power 2, 10 to the power 10 solar mass black hole. Just from the Eddington limit argument, one can say that there is a huge mass. Okay, on the other hand, we have the variability time scale, which are very short. And we just saw the X-ray variability time scale translates to very, very compact size, something like 10 to the power minus 5 parsec or so, which is of the order of Schwarzschild radius for 10 to the power 8 solar mass. So we are from large luminosity, we are inferring a huge mass, 10 million, more than a million solar mass. And from X-ray variability, we are inferring that the size should be of the, let's say, of the order of the Schwarzschild radius for the million or billion solar mass. So what this means is that, what this implies is that there is a supermassive black hole at the center. Of course, if it is a black hole, the size is very small, as we essentially will be given by the Schwarzschild radius also. So if a black hole is sitting, then of course it will accrete material. And as a result of this accretion process, there will be energy released. And this is what is thought to be powering the huge luminosity or huge power output of active galactic nuclei. So the supermassive black holes sitting at the centers of galaxies, if they are accreting material, then they are producing huge luminosity, what we are observing in different bands. So to summarize, the picture we have is the AGNs have a central supermassive black hole, which may or may not be rotating. The mass of the black hole is about 10 to the power 5 to 10 to the power 10 solar mass, and they are powered by accretion. So the accreted power is being converted into luminosity with an efficiency eta. So in this efficiency, you can think it is roughly about 10% or so. In fact, much higher than the efficiency for nuclear reactions. And that is why the nuclear reactions are not supposed to be the source of power that we are observing here. But the accretion power, the accretion is powering the AGN, which is more efficient than the nuclear reactions. The size of these things you can think, imagine in terms of the Schwarzschild radius. The luminosity is comparable. I mean, you can think of in terms of Eddington luminosity, given with this expression. So these are the simple things to remember when we discuss more about the AGN physics. Okay, so I described to a number of properties in the optical spectrum. Even we will see the X-ray spectrum. We have seen the spectral energy distribution. So how do you fit everything into one paradigm? So there is so-called the AGN unification scheme at, let's say, AGN paradigm, where all these observations in very different bands from radio to gamma rays can be fit into one picture in one paradigm in a way. So in this paradigm, at the center of an active galaxy, there is a supermassive black hole which is accreting, and because this accretion forms an accretion disk. Okay, and that we will see that. So this accretion disk emits in the optical ultraviolet band here, and that's what we call the big blue bump emission. Okay, then then in the inner region, so there is something called there is a hot corona, and since hot corona is essentially a very compact region consisting of very energetic electrons. And the temperature of this hot corona is thought to be about a few hundred keV, something like 10 to the power 8 Kelvin or so. So that then the optical EV photons from the accretion disk are interacting with the energetic electrons, and that process is called Comptonization, because there the inverse Compton scattering dominates, and this Comptonization process is thought to generate the X-ray emission what we observe. The optical UV emission from the accretion disk, the X-rays due to the comptonization, all of them are actually interacting with the surrounding medium, and there are lots of these different kind of entities here. First of all, very close to the I mean in the very close to the disk, there are this line emitting clouds. These are called broad line clouds, and these are the clouds which are giving rise to these broad emission lines here. Further away from broadline region. They're much further away. In fact, the broadline region size is something like 0.01 parsec. But if you go to 100 parsec or more than that, then there are other types of clouds which are called the narrow line region clouds, and they are giving rise to the narrow emission lines. So the clouds which are closer to the black hole are moving faster. That is why they are giving broad emission lines where the speeds are something like 5 to 10,000 kilometers per second. While the narrow line region clouds are much further away, they are moving only with speeds of few hundred kilometers per second. And in some regions, we do not observe this broad emission lines, and that is due to the structure called dusty torus. So this dusty torus, the role of dusty torus is to essentially absorb this radiation, optical ultraviolet radiation and X-ray radiation, if our line of sight passes through this dusty torus. So if our line of sight is passing through this dusty torus, we do not have a view of the inner central engine, including the broadline region, and therefore you do not see broad emission lines. What you see is this narrow emission line region, and therefore only narrow emission lines only. But on the other hand, if your line of sight does not pass through this torus, but in that case, we have a direct view of the central region. So we observe very strong X-ray emission, very strong optical UV emission, and the broad emission lines from the broadline region, as well as narrow emission lines from narrow line region. So you see the full strength of all the characteristic of these agents when our line of sight is appropriate, or when our view to the central region is appropriate, and the spectrum is much more complex. The dusty torus is actually absorbing the radiation, the ultraviolet, optical ultraviolet radiation, as well as X-ray radiation, and it reprocesses. Essentially, it gets heated, and it is a thick material, so it emits more like black body. But because the temperature is much lower, it is emitting in the infrared, and this part is called this infrared bump, is essentially due to this dusty torus. And I have mentioned the X-ray emission from the innermost regions, but we will look into in little more detail about the inner regions here. So how does the innermost regions look like? We of course do not know. We cannot resolve and take a picture of the innermost regions, but from the studies of let's say the time variability, the spectroscopy, etc. So from those studies, what we think that the innermost regions of agents may look like this. First of all, there is a supermassive black hole, and surrounding the supermassive black hole, there is this accretion disk here. Accretion disk, the temperature of the accretion disk in the innermost regions is high, so that it emits in the extreme ultraviolet or so. But when you move away from this accretion disk, the temperature decreases, and the intermediate regions emit the optical radiation. Outer regions will emit infrared, finally cutting the emission at 1 micron or 1 micron or so. Then there is some kind of a corona, and we do not exactly know what is the geometry of this disk and corona, relative geometry of the disk and corona, but it is possible that this corona is the base of the relativistic jet. Relativistic jet is emitting our radio emission as well as other emission at other wavebands sometimes. But this base of the jet probably is the hot corona, where this hot, which contains these highly energetic electrons. Then the optical UV photons from the disk will interact with this energetic electrons, and that gives rise to X-rays, and we will see how that can happen. But this is one possible configuration, but there are other possible configurations. For example, this one, we may be having particularly in radio quiet agents, because radio quiet agents, we do not observe strong jet emission, so there may not be a strong jet here. But in such cases, the corona, hot corona, may be roughly spherical region surrounding this black hole, and in the on top of this innermost accretion disk. Even in this case, the photons from the accretion disk will interact with the hot corona and give rise to X-ray radiation. So these are some of the possible geometries, and a lot of research is still going on to understand the innermost regions in the immediate vicinity of the supermassive black hole. Okay, so let's discuss again the spectral energy, the very different components in the broadband spectra of AGNs. The most important component is the big blue pump, which is thought to be the direct result of accretion onto the supermassive black hole. So as the material is being accreted onto supermassive black holes, the material cannot directly come radially and disappear below the event horizon of the telescope, because the matter being accreted has certain angular momentum, and the conservation of angular momentum forms this accretion disk, where the matter is mostly spiraling around the supermassive black hole, and gradually it is spiraling into black hole. So therefore it is gradually falling onto the black hole. Otherwise it is moving roughly in Keplerian orbits. So such a disk is thin, geometrically thin, and optically thick. So what that means is that if you divide the accretion disk in a large number of annuli, then each annuli will have certain temperature. The temperature in the innermost region of the disk is highest, and when you move outward, the temperature decreases is radius to the power minus 3/4. So if you consider the various annuli, then each annuli the emission from each annuli you can approximate black body like at the temperature of that annulus, and therefore there will be a large number of black body emission from all these annuli, and finally you sum the black bodies from different annuli and you get the total spectrum of from the accretion disk, which of course will be much broader compared to the individual black body emission. And the emission from the accretion disk will cut off at high frequencies because because of the emission from the inner region, which has the maximum temperature. Beyond that, accretion disk does not exist. So therefore, the spectrum cuts off. So one can actually measure this, observe this spectrum, the accretion disk spectrum, and model according to this prescription, and then one can find the temperature profile and study accretion disk. Okay, so the result of accretion onto the supermassive black hole, we have this optical ultraviolet continuum emission, which is shown here. And the accretion disk models actually tell us this what exactly is the shape of the spectrum. For example, in the optical UV region, the continuum is more like a power law with a spectral index of 1/3 or so. Then it, of course, cuts off. But the accretion disk alone cannot explain the other components. For example, the high energy radiation, particularly the soft and hard X-rays, because the accretion disk has some temperature distribution, and that due to that it cuts off in the extreme ultraviolet or so. So we need other radiation processes to account for the X-ray emission, the soft and hard X-ray emission. So this is another way of showing that how. So here you see, okay, here you see the accretion disk component, which is shown here, continuum, and then on top of this large number of emission lines from broad line region, narrow line region, etc. And then there is a X-ray power law component in between this. Let's say far ultraviolet to extremely soft X-rays. Essentially the XUV band or extreme ultraviolet XUV, many times we don't have access to this band because this band is affiliated with the galactic extinction, and we don't observe here. But of course the disk emission has to be connected with this X-ray continuum here, and this is the real observed spectrum in the optical ultraviolet, and here you 13.6 electron volt, and even the accretion disk is not able to model the spectrum satisfactorily. But of course, there are much more complicated physics, including extinction, host galaxy, contamination, etc. But it is roughly like the big blue bump, the accretion disk spectrum, what we observe. And then, of course, there is an X-ray power law, strong X-ray power law continuum emission. Okay, so observationally, how does the X-ray spectrum looks like? How much time I have? I think
Gulab, you could continue for about 10 minutes or so, 10, 12 minutes.
Okay, thank you.
Thanks.
So observationally, the X-ray spectrum of AGN looks like something like this. In the x-axis, there is the energy in keV. Now we do no longer measure in wavelength and frequencies, because here we are observing individual photons. So, and we are measuring the energy of individual photons, which in keV is a convenient unit. Then in the y-axis, we have photon flux, photons per centimeter square per second per keV. Here in X-rays, we measure individual photons. So that is why we measure, here we plot in terms of photon flux rather than the energy flux. And these are log scale. So any linear line will have a power law spectrum. So, and these are the observed data. For example, the one in the red is the observation X-ray spectrum of this AGN called PG 1416 minus 1 to 129. So this is roughly like a linear line, but there are certain departures. First of all, at high energies, about 100 kV or so, the spectrum cuts off. It does not continue as a linear line or like a power law here. At lower energies, there is some kind of an excess emission, which we call as the soft excess emission. Okay. Otherwise, the X-ray spectrum is essentially dominated by a power law, which we can write something like this. The NE is our photon flux plotted in the y-axis, and the power law is e to the power minus gamma. And this gamma is now called photon index rather than the spectral index, because we are measuring the photon spectrum here. So e to the power minus gamma, and gamma is the photon index, and a, of course, is some normalizing factor. So this
question.
Yeah.
Could you explain spectral index and how is it useful, etc.?
So when you are measuring the flux in energy units like ergs per centimeter per centimeter square per second per unit frequency, that is called F nu, the flux density, and measured in energy units. Then if you plot that as a function of frequency, then you write that as a spectrum F nu proportional to nu to the power minus alpha. So that is the energy, the spectral index, energy spectral index, you can call. So radio astronomers, for example, will use that kind of convention, while the optical astronomers use F lambda, flux density again, but this time ergs per centimeter square per second per angstrom, plotted as a function of angstrom, and they will write like F lambda is proportional to lambda to the power let's say minus p or something like that. So in that case, this p, again, that is called a spectral index, but for wavelength space, let's say. And the energy spectral index, when you're using frequency units, alpha and gamma, all these are related quantities, but they're used differently. But the shape of whether it is photon index or the spectral index, the shape of the spectrum is related to the physical process, and that's why measuring whether it is a power law like or black body like or some different shape is crucial. The first thing is to measure the shape of the spectrum, then we think about the physical processes occurring.
Okay, thank you.
Yeah. So how do you produce this power law which is dominating? The other AGN, which is NGC 4151, there is again a power law at least above a few kV. It is like a power law, and so cutoff again at few hundred kV. At low energies, the spectrum is cutting up, and that's due to absorption. The soft X-rays are getting absorbed, and that is why this emission is cut off. If there were no absorption, the spectrum will also continue something like this. Okay, that's the only difference here. So the question is, what is the process which is giving rise to a broadband X-ray power law from few kV to all the way to few hundred kilo electron volt, and then cut off? So what is the origin of this power law which cuts off at about 100 kV? And that process is known as the componization in a hot corona. And to understand this one can assume this two-phase model. One phase is this accretion disk, and accretion disk temperature is something like 10 electron volt. Of course, it will depend on the black hole mass, but assume this is a 10 electron volt or so. So it is emitting in the ultraviolet and optical bands. Then we have another phase is the hot phase, which is the hot corona, and a temperature of about 100 kilo electron volt. It is usually optically thin. So essentially this has energetic electrons, and this has optical UV photons. And then optical UV photons are interacting with this energetic electrons. So naturally there is going to be inverse Compton scattering and repeated inverse Compton scattering. So that repeated Compton scattering is essentially resulting in the power law, broadband X-ray power law, in the following way. Let's say this disk is emitting roughly like a black body emission. Okay, and this black body spectrum is interacting with this hot corona. So in one scattering step, let's say, what is happening? A fraction tau, which is tau, where is the optical depth of this corona, that fraction, you take the fraction which is tau is less than 1, you take that fraction which this black body reduces to by this factor, then this is upscattered due to inverse Compton scattering. So this black body, reduced black body, actually moves at higher energy in one scattering step. And imagine the multiple scattering steps, and every time the strength is reduced and then pushed to higher energy, reduced and pushed to higher energy, until the energy of these photons reaches close to the temperature of these electrons in the hot corona. And then you sum all these black body components, then it looks like a power law which cuts off at few hundred keV. And this is a very basic physics which is giving us a broadband X-ray power law which cuts off at the temperature of the hot corona, or KTE, you can say. And if you want to know more about this, these are the papers you can actually read. Okay, and there are observations, probes. This is observation from a NASA mission called Star, and the Japanese mission Suzaku. This is, and you see, this is this data is actually the ratio of data to model, and model is a simple power law, and you are comparing this data. So this is ratio, and beyond, let's say 20 kV or so, this emission is actually reducing. And this reduction emission about above 20 kV or so is actually the source signature of the cutoff in the spectrum. But if you introduce a cutoff, then you can model the data reasonably well, and that's how you measure the temperature of the corona. Okay, if you look at the X-ray spectral energy distribution, of course, again, this is in log-log plot, the photon flux in log unit, and energy in log unit. So so a constant here, in fact, it is new EFE. EFE was plotted as a function of energy. So here a constant line will result in a power law with a photon index of 2. So the entire emission is dominated by a power law with a photon index of 2. Okay, but then there are departures. Of course, there is an excess emission, soft excess emission. There are a large number of these absorption features. Here, this is again a schematic picture, not even a model, but in schematic picture, there are some absorption lines are shown. Then there is this iron K alpha line, which can be broad or narrow. There is a hump-like thing, and then at higher energies there is a cutoff. So the X-ray spectroscopy, the aim of the X-ray spectroscopy is essentially to understand these components and connect to the agent central region and probe what kind of things are going on in the immediate vicinity of the supermassive black hole. So I'm not going to in very detailed, but just to explain a few things, why there are so many absorption features, let's say. So this is the real spectrum, nearly 900 kilosecond, roughly about 11 days, 10 or 11 days of continuous observation with the Chandra Observatory by NASA. and you see huge number of this absorption. It looks like noise, but they are actually real features. There are numerous absorption features, and that these kind of features is due to there's some kind of an absorbing cloud which is absorbing and giving rise to this numerous absorption lines. The radiation from this hot corona central region is passing through some kind of a cloud, and this is giving rise to huge number of absorption. So why there's so many absorption line in the optical spectra? You actually saw, okay, there are H alpha, H beta, H gamma, etc. But lines are well identified and not blended like this. The reason is that in the X-ray band, for example, you think of the iron K band, which starts at 6.4 kV to 9.1 kV or so. So in that band, just look at the iron. Iron has 26 electron. So the neutral iron will give rise to an emission line at 6.4 kV. And hydrogen-like iron, that means all electrons except one has been removed, is the hydrogen-like iron will give rise to an absorption feature at a 9.1 kV. So now imagine neutral iron, 26 electrons, hydrogen-like iron, 1 electron. And in between, there will be lots and lots of ionization stages. So each ion will have its own energy level diagram. So each ion will produce number of absorption lines, and the large number of ions will produce huge number of discrete features. That's only from iron. Now you think of all these elements which have their K-cell energies, K-cell bands in this energy band, soft X-ray band 0.2 to 10 kV. So this is a large number of elements and a huge number of ionization stages, and the energy level, very different energy level, levels of each of these ions will cause huge number of transitions, and that's why we get huge number of this absorption lines. Okay, I think I will skip this. So I'll only in the next couple of minutes, I will only mention one more thing. This is the iron line. So in AGN spectra, we observe the iron K alpha line, which sometimes is very broad. If you recall, I had mentioned that the width of optical emission lines is about 5,000 to 10,000 kilometer per second or so, the velocity width. And here in the X-ray band, we see the line width up to something like 50,000 kilometer per second or even higher. So the iron K alpha line emitting material in the X-ray band is actually moving much faster, and naturally it has to be closer to the supermassive black hole. So therefore, this line can be used to probe the inner regions very close to the supermassive black hole, and to look into the very basic physics of this. So let's consider this picture. So this, the X-ray radiation, the power law, broadband X-ray power law radiation is arising from this hot corona due to repeated inverse Compton scattering. The power law is also illuminating the accretion disk. Now these X-ray photons, which are high energy photons, are interacting with the material in the accretion disk. And this material, this accretion disk temperature is about 10 electron volt or so. So maybe some of the hydrogen, helium, or maybe partially ionized, but otherwise the disk has a lot of atoms as well, heavy atoms. So the X-rays photons will interact with this atoms and partially ionized material here, and then they will. Okay, so for example, you consider one iron atom. So the photons, X-ray photons with energy more than 7.1 kilo electron volt will knock out the electrons in the innermost K cell, and they'll produce one vacancy here. In such a stage, of course, unstable state, there's therefore an L cell electron will jump to K cell and giving rise to this characteristic K alpha line emission. Similarly, there are other elements which will also produce similar lines. See here, the simple picture is there is a power law continuum like this, which is illuminating the accretion disk, and then the accretion disk is giving rise to this kind of spectrum, which we call the reflection spectrum. Among the features, the iron K alpha line is the strongest due to the large cosmic abundance as well as high fluorescence yield. And this line is modified due to the spatial and general relativistic effects near the supermassive black hole. So imagine this is your accretion disk, and at the center there is a supermassive black hole. And now imagine there are two rings in the accretion disk, and you are observing line emission from these two rings. And because the accretion disk is rotating, just using Newtonian physics, the line emission, if you observe, it will look like this due to the blue shift and red shift. And now if we apply special relativity, because the speeds near this black hole can be relativistic, 0.1 times c or something like that. So then you have to apply special relativity. So there are two effects. One is relativistic beaming. For example, consider this part of the disk which is moving towards us. So that emission from the disk which is moving towards us, instead of going to all the 4 pi direction, because of the relativistic speed, it is beamed towards us. So therefore, the high frequency part is actually the strength increases because of the relativistic beaming, while the part of the disk which is moving away from us, there the emission is diminished because the radiation is beamed away from us. And then due to the transverse Doppler shift, the entire profile is shifted to a redward due to essentially this time dilation effect. So then because there is a supermassive black hole, there is a effect of general relativity, and one has to apply the general relativity, particularly the gravitational redshift, the light bending, etc. And this entire thing will redshift the line as a function of energy, and the line will be the photons at the red wing will be even more shifted towards low energy. And if you sum the line emission, it looks like something like this asymmetric line profile, double hump. There is a double peaked, one peak is here, another peak is maybe here. And this is the characteristic line profile, which was observed by the Japanese satellite called Advanced Satellite for Cosmology and Astrophysics. And this was a model fitted, and this was an interesting result. But because one can now use this broad iron caliper line to probe the innermost regions surrounding the black hole. So I think I will skip these things. This is another observation of a broad iron line. And you see in the rest frame, of course, this line will arise at 6.4 kV or so. Because of this effects of relativistic speeds and strong gravity, the line photons are actually being shifted from about 6.4 kV to all the way to 4 and even 3 kV. And such an emission, such a strong red wing is observed due to the emission from very close to the black hole within few RG. Because this is how one can by measuring the inner edge of the disk using this red wing, one can measure the inner radius, and from the inner radius one can measure the black hole spin. Because if the black hole is not rotating, then the accretion disk can extend only up to 6 times gravitational radius, while if the black hole is maximally rotating, the accretion disk can go down to about 1 RG. And if it is going very close to the black hole, that means the effect of spatial and general relativity will be much more stronger, and the line will be shifted to even lower energy. And that is what is happening here. And there are a lot of things, additional things, additional studies are going on at the moment to probe the innermost regions. So thank you. I will stop here. I could not complete some of the things which I wanted to mention, but here I list some of the books which you can look at if you want to understand, or if you are interested to study the central engines of active galactic nuclei. Thank you very much.
And thanks very much, Gulab, for a great talk. So you all can unmute and ask your questions or raise your hand, whatever you like. Or even put it in the chat box if you have audio problems.
You said that black holes accrete material, like the central black hole accrete materials. And also you said that the radiation pressure will cause materials to throw away. So my question is whether the agent will help in star formation or will prevent it.
Yeah, this is a very good question. So when the AGN is accreting, then some of the material is being thrown out, of course, in the form of winds, outflows, and jets, which are interacting with the host galaxy material. And there are studies, there are a lot of people actually studies this feedback, Asian feedback, and the effect of this interaction of the winds, outflows, jets with the host galaxy. And what people find that these things arising from the Asian can cause star formation, enhance star formation, and in some conditions they can also suppress star formation. So this is another very interesting area, and a lot of people are working on this Asian feedback and how does it affect the host galaxy. In fact, one of the major thing is so-called the M sigma relation, where the M is the black hole mass and sigma is the stellar velocity of the essentially the motion of stars. So these two things are actually observed to be strongly correlated, and this is why people think that the central black hole will be affecting the host galaxy, and they are probing why this relation is there through the Asian feedback and various things.
Okay, thank you, sir.
Yeah.
Maybe one more question, Sanyukta, and then we will take a break.
Yes, so I wanted to know, like, since like Asians, so they must have very large diameter disk. So can star formation occur, or like stars be ripped apart in that accretion disk?
Yeah, so this is another very interesting question and not fully understood problem. But there are people who have studied star formation in the outer accretion disk. I'm not really an expert on the star formation, but there are studies, and some people think that the stars may be forming in the outer regions of the disk. Maybe Professor Sakya can find out. He's an expert in the Asian physics as well. Yes.
So you want me to add to that, Gulab? This is on star formation, right?
Yes. So the question was whether the accretion, there can be star formation in the accretion disk itself. So I know some people are working on the star formation in the disk, and they think that the stars may be forming in the outer regions of accretion disk.
Yeah, that's right. Actually, outer regions it could be, but inner regions it would be difficult actually.
Yeah.
Will the temperature and densities be appropriate for that? Because the outer region of the accretion disk is still reasonably close to the rest of it, right?
Actually, it goes and merges sort of with the torus and all that, right? Which is molecular gas.
Yes.
Okay.
So it depends on how far you extend it.
That's where the reservoir is.
Okay.
Yeah. I mean, one of the big problem in how do you extract the angular momentum of the material which is being accreted so that the material moves inward. And it is possible that the star formation may be resulting in loss of angular momentum in the outer accretion disk. Of course, there has to be other processes in the inner region, but these are a bit complex. Not.
Yeah, there are actually viscous forces, turbulence, all that would also play a role in dissipating angular momentum, some of the material going outwards, some of it falling inwards.
Yes. So inner regions, of course, there are other processes, but in the outer region, yes. I mean, all those magnetic processes require ionized or partially ionized material, but in the outer region, if it is more like a molecular gas and all that, so that process, the same process may not be effective there.
That's right. Yeah. Okay, Gulab, thanks very much.
Thank you very much.